Now that we've seen the inverse tangent function, we're going to find a power series representation for the function f of x equals the inverse tangent of x cubed, and we'll determine the radius of convergence. Well, f of x is equal to x squared times the sum as n goes from 0 to infinity of negative 1 to the n divided by 2n plus 1 times x cubed to the 2n plus 1. We're just using the formula that we developed. Now this exponent, x cubed to the 2n plus 1, that exponent becomes 6n plus 3. But we have a common base. We have x squared on the outside and x to the 6n plus 3 inside the summation notation. So combining those bases is going to give us the sum as n goes from 0 to infinity of negative 1 to the n over 2n plus 1 times x to the 6n plus 5. For the radius of convergence, we will use the ratio test. We've got the limit as n approaches infinity of x to the 6n plus 11 divided by 2n plus 3 times 2n plus 1 divided by x to the 6n plus 5. That is in an absolute value. All but 5 factors of x will divide out. And we're probably getting pretty savvy at this point that 2n plus 1 over 2n plus 3 is going to have a limit as n approaches infinity of 1. So this effectively becomes the limit as n approaches infinity of the absolute value of x to the 5th. This converges if the absolute value of x is less than 1, which means that the radius is equal to 1. Now let me box up the answers, and there we are. Next, same idea, but a different function. Our function is f of x is equal to the quantity x over 2 minus x cubed, which I'm going to express as x cubed divided by the quantity 2 minus x cubed. Folks, if this was actually 2 minus x cubed, not the quantity, but 2 minus the cube of x, easy peasy, wouldn't have a problem. But we have to deal with the fact that we have this binomial 2 minus x that's cubed in the denominator. The x cubed in the numerator we can deal with, we pull it out, we're going to add 3 to whatever exponent we have on x. So that's not an issue. This requires a little bit of ingenuity. And here's how it goes. If g of x is equal to 1 over 2 minus x, now that's something I can find a power series for, but it's also something that I can differentiate. For that g, we have that g prime of x is equal to 1 over the quantity of 2 minus x squared. Ah, you see, we're getting there. We have a squared down here. We need a cube. So what should we do? Probably differentiate again. And g double prime of x is going to equal 2 divided by 2 minus x, the quantity cubed. You may be asking, what happened to the negative sign for the exponent? The inside function is 2 minus x. Its derivative is negative 1. Every time we differentiate, the two minuses will offset each other. What this means, though, is that we can find a power series for 1 over the quantity of 2 minus x cubed by differentiating twice. And then when we're done with all that, we'll bring in the x cubed that's in the numerator like we're supposed to. Oh, one more thing I almost forgot. Here we have g of x is equal to 1 over 2 minus x. We need that to be a 1 minus x. So we're going to start out by saying that g of x is equal to, we're going to divide the numerator and denominator by 2. So we end up with a 1 minus down there in the denominator. So g of x is equal to 1/2 divided by 1 minus x over 2, which we know is equal to 1/2 times the sum as n goes from 0 to infinity of x over 2 to the n. We are replacing the base of x in our foundational example that we were looking at in some other videos. So g prime of x then will become 1/2. Now we're going to use the power rule, times the sum of n over 2 to the n times x to the n minus 1. That power rule says bring the exponent out front as a factor, and then drop 1 from the exponent. The index needs to increase by 1 each time we differentiate, so the sum is going to be as n goes from 1 to infinity now. We've already noted we need to differentiate twice, so we're going to roll that again. So we have g double prime of x is equal to 1/2 times the sum of now n goes from 2 to infinity of n times n minus 1 over 2 to the n times x to the n minus 2. Now, we've just developed that expression as representing g double prime of x, but folks, a few minutes ago, we said that g double prime of x was 2 over 2 minus x, the quantity cubed. Therefore, I can say this equals 2 over the quantity of 2 minus x cubed. And we are getting pretty close to what we're after, but we differ in a couple of key ways. One, what we were after was x cubed over 2 minus x, the quantity cubed. And we're going to bring that in that x cubed. But the other thing is, here I have a 2 in the numerator. I should not have that. So we're going to divide both sides of this by 2. X cubed over the quantity of 2 minus x cubed will then equal x cubed over 4 times the sum as n goes from 2 to infinity of n times n minus 1 over 2 to the n times x to the n minus 2. So again, we divided both sides by 2, turning that 1/2 into a 1/4, multiplied both sides by x cubed so that we'd have the expression that we were after. Now we can do a little bit of cleanup by combining common bases. We have 2 squared in denominator outside. We have 2 to the n inside of the sigma notation. So we can say that this is equal to the sum as n goes from 2 to infinity of n times n minus 1 over 2 to the n plus 2. It's the result of combining the bases of 2. But folks, we can further combine. We can combine x cubed with the x to the n minus 2. That's going to give us x to the n plus 1 by adding 3 to that exponent. Now, we could leave this like this, but our index starts at 2. We can make that index start at 0. So I'll wrap this up by x over 2 minus x, the whole thing cubed. That's what we started out with, right? Oh, and they called it f of x, so let's do that. Is equal to the sum as n goes from 0 to infinity. Now what I've done is drop that index by 2, so I need to increase all of the instances of n by 2. We'll end up with n plus 2 times n plus 1 divided by 2 to the n plus 4 x to the n plus 3 as the argument of the summation notation. As for the radius of convergence, I will let you verify that the ratio test will show that r is equal to 2.